So I want to introduce the chain rule and also go through a few examples. So we have, a few basic tricks for derivatives. We know that the derivative of something like x to the n is going to be n times x to the n minus 1. And we also know, the derivative of e to the x is just e to the x. And a few other basic things, like you might know the derivative of log. You probably know the derivative of the cosine and sine, the derivative of the trig function. So for instance, the derivative of tangent is secant squared, and so forth. And we also have ways of finding the derivative. So basically, what you want to be able to do is take the derivative of any expression by somehow really only knowing these fundamental derivatives that were kind of hard to establish. And so we know rules for finding the derivative of combinations of functions. So what's an example of a combination of functions? So if you have x squared times e to the x and you take its derivative, you know that you can find the derivative of this combination by using the product rule. You just think of this as one part and this is another part. And then just knowing these basic fundamental rules together with the product rule, you can easily find this derivative without going back to the definition where you take the limit as h goes to 0 of that terrible expression. You don't want to have to do that every time. So all right. So another way to combine functions is to take their composition. So these two functions are just multiplied together, but you could also sort of compose them. So if I use e as the outer function and x squared as the inner function and compose them, then I get e to the x squared. So this is the exponential function composed with the square function. And if you take its derivative, you want to be able to, just like in the product case, not go back to that crazy definition where h goes to 0 and so forth. And you want to think as little as possible. So the chain rule helps you do that. So there are lots of different ways to say how the chain rule works, but the way I've had the most luck explaining it is just to imagine, being able to see the outside function and the inside function is one of the hardest things to explain. So I hope you can see that this whole function is really just something of the form, it's e raised to some blob power, and the blob here is not the variable. But when we take the derivative, we want to kind of pretend like it is the variable, because we know the rule for taking the derivative of the exponential function. And so the chain rule says that you can do this, just take the derivative the way you normally do, but you have to pay a price for simplifying things in that way. And the price you pay is that you have to multiply by the derivative of the thing that you pretended was just the variable. And we're done. It's just that we have to work out exactly what w prime and w are, go back to the original variable x. So what is it we were actually doing here? When we made the simplification of going to w, we were saying that w is equal to x squared. So, to put things back the way they should be, w is really just x squared. So here we have x squared. And now we also owe w prime. What is w prime? Well, that's just the regular derivative of x squared is 2x. And so we write 2x here, and that's it. So the derivative of e to the x squared is e to the x squared times 2x. Let's do another example. I'm going to hopefully do a ton of these. So let's do y is equal to sine composed with x times cosine of x. Right? Okay. So this is the kind of hard, unteachable part that comes with practice. By the way, if you haven't done this literally about 30 times, then you aren't really trying. You need to sit down with the book and just do basically all the problems. That's the way you learn how to do this. And if you're not doing that, then it's not surprising that you can't use the chain rule, because you haven't tried to learn it yet. So I hope you enjoyed the sermon. This is basically sine of some blob. So when we take the derivative of sine is cosine, and the blob stays the same. Okay, ha ha ha, it was so easy. But now what we have to do to make up for that simplifying assumption about the inside just being this one variable is multiply by w prime. Now what we have to do is figure out what the hell we just did. So we're done. And so what is this w mess? Well, let's think about what we really did. We said that w is equal to x times cosine x. And so w prime is a product rule problem. Take the derivative of x first and you get cosine x. And now plus x times the derivative of cosine is minus sine x. Okay. And now you have to sort of put it all together. So just rewriting everything here in terms of x. This is cosine of x cosine x. And this w prime is, be sure to do quantity times, is cosine x plus, I guess maybe it should be minus. Use minus. Minus x times sine x. And that's it, we're done. Okay, so no problem. Now let's keep going. I know you probably have a powerful hunger for the chain rule. What about this one? This one is still not too hard. We'll do y equals x secant kx. Okay, so this one has gotten a little bit crazy because there's a constant k in here. So k is just standing for some number, and the variable is x. And maybe in this case it's good to emphasize the fact that we're taking the derivative with respect to x, because that kind of explains why we treat x and k differently. So here k is a constant. And so, you know, I could write y prime here, but just to remind you about why x and k are treated differently, y prime is really standing for the derivative of y with respect to x. So I'll take the derivative with respect to x of both sides, and so here it's x secant kx. Okay, right? So what's the basic form of what's going on here? This is the part that's very hard to teach. You have to see this as a product of two functions, and if you can't see that, I don't know how to put the chunking power into your brain where you can kind of simplify this and just see it as the product of two things. That comes from doing the problems 30 times. And if you can't do it, the reason is that you need to do this about 100 times. So I guess maybe 1,000 times or 2 million times. Alright, so if we take the derivative of this thing, we know that it's really just f prime g plus f g prime, because we know the product rule. And we're done, except that now we have to figure out what the hell we just did. So what did we just do? So f is x, so that's not very hard to understand. So f prime is just going to be 1, so we can write this as, you know, f prime is 1, so this is really just g, and f is x, and now should write g prime here. So now we have to figure out what's going on with g, so let's just do that kind of off to the side. So g is secant kx. So what should g prime be? Well, this is where the chain rule comes in. We haven't used it yet. So g is really a function of the form, you know, secant of some stuff. And so what is g prime going to be? The normal derivative of secant is secant times tangent. So if I take the derivative, it's just secant w times tan w. Okay, but I treated this complicated thing as if it were just a variable, and now there's hell to pay. And you do that by putting in w prime. That's all you have to do. It's really, the universe is really not as mean as it could be. So what does all this turn out to be? Just go back to what w was, which is k times x, and you see that g prime is equal to secant of kx tangent kx, and the derivative of kx is, with respect to x, k is a constant, so the same thing happens to this that would happen to like 2x. You know, the 2 would just be left over. For the same reason, you just get k. And let's put it all together. So where were we when we left off? We were right there. So let's go ahead and finish. And so this should be secant kx plus x times all this stuff. Since I'm using a computer, I could just cut it and paste it like this, and we're done. Okay, so g prime goes there, and that's the end of the problem. And just to remind you what we were doing in the first place, this is dy dx, also known as y prime. Okay, so let's do a few more. You've noticed probably that as we go along here, there is more going on than you can keep track of in your head. And the only reason that we're able to do it is because we carefully write things out as we go along. And as I teach students to do this, I get really frustrated because you guys are really reluctant to write things on a new line. You know, you want to solve some equation like let's say 2y plus y squared equals 17, and then instead of writing a new line of stuff, you start doing well, this, what am I even doing here? Let me change this a little bit. Yeah, so let's say it's like this, equals 7, and then, you know, you start doing this, and you say the y goes here, and then you divide both sides by y or something like that, and then you do a bunch of other crazy crap without going down to the next line, and all of a sudden you don't know what the hell is going on, and I don't know what the hell is going on either. You have to use the page to augment your brain. You can't do it all in your head, and you can't do it all in one line. You need to not be afraid to burn some paper. Okay, so let's do one that's a little bit harder now. And I'm going to start doing them faster without all the explanation. So f of z, f is a function of z. Whoa, don't want that thing. Go away again. So f of z is equal to the square root of z minus 1 over z plus 1. Okay, and so this is all something to the 1/2 power. So now I'm going to do it sort of without comment, and this is the way you'll start doing it when you've practiced it enough. The 1/2 comes down, and you leave the stuff alone inside, and here you've got z plus 1 on the bottom. This becomes a minus 1/2. Okay, and now you have to do times the derivative of the stuff on the inside, and that is a quotient rule problem. So take the derivative of the top thing first, which is 1, and multiply it by the bottom thing, so that's just z plus 1. Now minus, leave the top thing alone, and multiply it by the derivative of the bottom, which is 1. And now you've got z plus 1 squared down here. And you can see that this stuff simplifies. Here you've got what's going to happen, these z's are going to cancel, and these 1's are going to become 2. So just in the interest of time, let me sort of excise this thing, if that will work. Who knows what this is going to do. Okay, it wasn't too bad. And so this stuff is all equal to you know, z, and now I'm doing it like a student, right? Just write crap all over everything until you can't understand anything. So what was it? It was like this. This is, I lost my parentheses, so this is the same thing as 2. So I'll just write 2 up here. All right, and that's it. And so let's do another one. So I know I'm going fast, but like I said, the way to do it is not to think hard about one example. The way to learn how to do this is to do it 100 times so that you do it without thinking. Um, if you're thinking very hard when you do this, then you haven't done it enough. When you play tennis, somebody hits the ball toward you, you don't sit there and think real hard about what you're going to do and try to, work out where the ball is going to go and scratch your chin. You just play tennis. All right, so this one is a little bit hard. So think about this one as just sine of some stuff. And so let's take the derivative, and it's going to be cosine of w times w prime. And now I'm doing this with the letters now because I have to, because I can't keep track of it mentally. So w is standing for this, and now you do w prime, and so this thing is itself, sine of some stuff, so use another letter. So if you take the derivative here, it's going to be minus cosine, sorry, it's not minus cosine, it's positive cosine of u, and then times u prime. Okay, so let me just slow down here because I know that was a little tough. So we got the answer. The answer is cosine w prime. Now we're in the stage of finding out what the hell we just did. We had said that w is this. We owe the universal y prime. So now we're busting our butt trying to deliver it. So we write w as what it is, but w itself is a composition of functions. And so to find w prime, we have to use the chain rule again. And so we're done with that, but now we have to figure out what the hell we just did. And so how did it work? What was u? U is equal to sine x. And so that means that u prime, now we're finally just down to the ground, is cosine x. Now what I have to do is carefully reassemble everything. So what is w prime going to be equal to in terms of x? It's going to be, w prime is going to be equal to cosine, u is sine x, and u prime is cosine x. Okay, so that's w prime, and now I'm ready to go back here and finally deliver the goods and write the real final answer. So it's going to be cosine of w, which is sine x. And here now I owe a w prime, and we just said that w prime is this stuff, so I should write cosine sine x times cosine x. And that's it. Okay. So I'm going to stop, because no matter how many times you watch me do it, it's not going to help. You have to do it yourself 10,000 million times.